The other day, we were talking about um, how the heat was transferred. And remember that we have three methods that heat can be transferred. Conduction, when you have, the heat transfer from particle to particle. And usually you're going to have a solid involved in there, even though liquids, when you're heating a liquid also, when the particles, they are colliding with each other, they are transferring the heat by conduction. Then you have convection, that mostly fluids are going to transfer the heat by convection. And then you have the last one that we were talking about, which was radiation. And you know that for heat to be transferred to radiation, you don't need matter. One of the samples that we were using was, the sun that is heating the earth just by radiation, because the heat transferred across the space by wave that are reaching the earth. Same happens when you are sitting around a campfire. The fire that you have, that fire is no matter. Fire is energy. So the heat that you feel in your face has been, transferred to you or to your body through radiations which move through the air, through wave in the air. We were talking about all of that, and you were calculating temperature conversions. You learn how to calculate, how to convert from Fahrenheit to Celsius, from Celsius to Kelvin, because remember that in the metric system, the unit of measurement used to express temperature is Kelvin. So what are you going to learn today? Today you're going to continue learn about heat, but how heat is transferred using different materials. That's why you have that over here, heat and materials. And then today you're gonna be able to calculate the energy that is needed, to heat up or cool down a given substance. These are the lesson objectives. You know that if by the end of the class you don't master the lesson objective, what's gonna happen? You're in trouble. See? So I'm going over the lesson objective. Over here you have that the first objective that you have to master after this lesson is that you need to know how to compare and contrast conductors and insulators. The second objective is that you have to analyze the information given by the specific heat of a substance. Okay, let's say that you know the specific heat of any given substance. You need to know what is the information that you can get from there. And the last objective that we want to accomplish with this lesson is that you have to be able to calculate energy gain and loss. In order to guide you to the learning process, I was posting here 3 essential questions, okay? Because let's say that you don't understand what the objective were explaining, or you don't understand like you don't know how to self-assess you to see if you master the 3 different objectives. If you can do that, so you can assess yourself, or you can assess your understanding, or you can check your understanding by answering the essential questions. And you have over here 4 essential questions. So by the end of the lesson, you have to be able to answer these 4 different questions that you have over here. Okay? The 4 different questions. And that's how you're gonna make sure that you are mastering the objective that we're presenting before. We are gonna start by reading your book over here, because your book is very good at explaining things at your level. Okay? So you have over here, the other day you were completing a vocabulary activity, that conductors are materials that they heat well, okay, meaning that they conduct the electricity very well. And you have example over here. It says metals such as silvers, they are good conductors. Let me tell you, because you don't know this, okay, that all transition metals, they are good conductor. Good conductors of heat. See, because we're talking about heat. They are good conductors of heat. Where can you find the transition metal? When you look at the periodic table, you're going to have, like 7 roads in the middle of the periodic table. So any metal that is located in that region, all of them, they are good conductor of heat. Okay? Because of the particles, because the way that the particles are arranged there. So it says most of the metals, they are solid. And you know that in solid, the particles, they are packed together. They are moving because they are vibrating in place, but they are close to each other. Once that the first particle is heating up, what's going to happen? By conduction, it's going to transfer the heat to the next one, to the next one, to the next one. And that's why metals, they are good conductors of heat, okay? Because we're talking about thermal energy. That's the first thing that you have to do, or that you have to know. Okay, conductors, they are good. They conduct, the heat very well. Okay, they're gonna heat up like quick. Also, here you have the definition of insulators. Okay, and I'm gonna use an analogy, but bueno, no, I'm not gonna use that analogy because you're not gonna understand that. I was about to use the pH analogy, but you're not going to understand that. Over here, you have another definition. Insulators, okay, are materials that do not conduct the heat well. Okay, Ms. Ramos, one of the objectives of the class is that we have to compare conductors and insulators. Conductors, okay, they conduct the heat well. See, very well. They heat up quickly. Insulators, Ms. Ramos. Insulators, they are gonna conduct the heat fast. No. See, they do not conduct the heat very well. Okay, do not conduct the heat very well. And I was explaining before that transition metals, they are good conductor of the heat, okay, because they're solid. But we have more material, we have more elements in the periodic table. And when we're talking over here about materials, we're not talking about elements, okay? We're talking about matter in general, okay? It doesn't have to be an element, but I'm using the elements so you can understand this better. In the periodic table, in addition to the metal that are mostly solid with one exception, which is the mercury, the non-metals and metalloids, they are solid, gases, and liquid, okay? And that's why the non-metals, they are not good conductors. They are not good conductors of heat. And many of the non-metals in the periodic table, they are good insulators because they are not good conductors of the heat. Okay, so I'm going to repeat that one more time because remember that you have to compare and contrast this. Conductors, they are conducting the heat very well. An example that you have, metals, okay? Transition metals, especially transition metals on the periodic table, they are good conductor of the heat because of the position of the molecules. They are solid, okay? Insulators, they do not conduct the heat at all, okay? They do not. Some of them that do that, but not very well. Okay, they're not gonna heat up like faster. They're not gonna cool down faster. So, insulators do not conduct heat very well, and non-metals. Most of the non-metals in the periodic tables, they are good insulators. Metals, good conductors, non-metals, good insulators. Okay? And I'm going to start the explanation of this part by reading what you have over here in your book. Okay? Imagine running across the hot sun and the hot sun towards the ocean. You run to the water edge, but you don't go any farther. The water is too cold. How can the sun be so hot and the water so cold? After all, the sun heats both of them. And I'm going to stop over there. What do you think happens? Why the water is so cold and the sun is so hot? And the first explanation that comes to my mind is that sun is a solid, yes or no, while the water, the ocean water, is a liquid. What's gonna happen in a solid? Heat is gonna be transferred quickly. Why, Miss Ramos? Because of the position of the particles. What happened to the particles in a solid? They are packed together. Now in the liquid, remember that they pass each other. So let's say that you have, a solid and liquid state are the same material. The solid stage is gonna transfer heat faster than the liquid one when you have the same material. That's the first explanation that comes to my mind. But we're gonna continue reading because remember that besides comparing and contrasting insulators and conductors, you have two more objectives that you have to master. Okay? The answer to the question that we had before is that water requires more heat to raise its temperature than the sun does. See, that's another explanation. I was using my background knowledge, see, when I was using the state of matter, but now your book is giving you more information. The answer is that water requires more heat to raise its temperature than sun does. See, what does that mean, Ms. Ramos? Que the water has to absorb or has to gain more heat to warm up than the sun. Okay. When a substance, I'm going to continue, or material is heated, its temperature rises. And you know that. Okay. When a substance is heated, you are increasing the kinetic energy of the particles. Consequently, the temperature is going to rise because temperature is the average kinetic energy of the particles. But the temperature doesn't rise at the same rate for all materials. You have the sample of the water on the sun. The amount of heat required to raise the temperature of materials depends on the material's makeup. Yes, depends. This is the part that I love the most because you know that I'm a chemistry teacher. See, the amount of heat required to raise the temperature of material depends on the material chemical makeup. Okay? Then I'm going to relate this with what you have learned before. If you have a material that is made of non-metals, so let me put that over here. Material that is made of non-metals. That material is gonna conduct the heat very well. So that material is gonna be able to heat up faster. I'm gonna leave that there for you to think. Different materials requires different amount of energy to have the same temperature increase. The amount of energy, this is the most important part. So the amount of energy requires to raise the temperature of 1 kilogram of a material by 1 Kelvin. See how you have, to convert your temperature into Kelvin here is called a specific heat. It is measured in joules per kilogram Kelvin. I'm going to write that over here. It's joule per means division, kilograms multiplied by Kelvin. That's the unit of measurement for a specific heat, where Kelvin is a measurement of the temperature. A material with a high specific heat can absorb or gain a great deal of energy without a great change in temperature. I'm going to say that in my own words. If you have a material with a high specific heat, you are going to need more energy to increase the temperature of that material. If a material temperature change, you can calculate how its energy change with a formula. And look at this beautiful formula over here. You're going to multiply the mass by the specific heat, which is a constant. And I'm going to give you the number, constant, multiplied by a change in the temperature. This table is in your book, and it's giving you a specific heat about, 4 different materials: aluminum, silver, and iron. They are transition metals. And then you have water, which is a compound. A compound is a combination of 2 more elements. Some aluminum, silver, iron metals. They are mostly solid. And then you have water, which is a liquid. And I want you to look at the numbers. Okay? Because I'm going to start writing over here. If you want, I'm going to start with the aluminum. If you want to increase, let's say, the temperature of aluminum from 25, 25 no, because it has to be in Kelvin. If you want to increase the temperature of aluminum by 1 Kelvin, let's say that you want to increase that from 273 Kelvin, which is 0 degrees. Okay, let's say that you want to increase the temperature of aluminum from 273 to 274. The difference is 1 Kelvin. If you want to do that for aluminum, you have to input in the system 900 joules. That's the information that you're receiving from the specific heat. The amount of joules you have to input or remove in order to increase or decrease the temperature by 1 degree of that substance. And I'm going to write that down. Information. This is the information given by the specific heat. A specific heat. Amount of joules. You know the joules is the unit of measurement that we use for energy. So joules means energy. Amount of joules needed to increase or decrease the temperature of a substance by 1 Kelvin. Like the sample that I was explaining to you before with the aluminum. They say that I want to increase the temperature of aluminum by 1 Kelvin. So I have to add this amount of joules. But let's say that I want to decrease. Let's say that I want to do the same, but instead of increasing the temperature of aluminum, I want to decrease the temperature from 286 Kelvin to 285 Kelvin. I need to remove I need to remove 900 joules from the aluminum. See? When you are increasing the temperature, you have to add that amount of joules. When you are decreasing the temperature, you are removing, no adding, you are removing the same amount of joules. And that's the information that you get from a specific heat. Okay. Also, I want you to look at the pattern over here. Aluminum, silver, and iron. AG, I forgot. AU is silver. No, that's gold. AG is silver. See? That's the symbol of the element. And then you have water. Water is made of hydrogen and oxygen. Both of them, they are not metal. Remember what we were talking at the beginning? Metals, they are good conductors of heat. Non-metals, they are good insulators. I'm going to repeat that again. Metals, good conductors. Non-metals, they are good insulators. Remember that? I want you to look over here. See? Look at the specific heat of the metals. See that? A specific heat. Let's say that you want to build a good conductor between the aluminum, the silver, and the iron. Which one are you going to use? I'm going to leave the question over there. Which of them is going to conduct, okay, the heat better? I know that all of them, they are good conductors of heat. But which one is going to heat up faster? What do you think? But of course, it's going to be the silver. Because it's the one that is using less energy. Okay? Less energy to change the temperature by 1 degree. Let's say that I want to make a pot. We call that in Spanish a caldero. I want to make a pot, and I have 3 materials. I have aluminum, I have silver, and then I have iron. Which is the best materials to build a pot? Of course, it's silver. But you know what happened with the silver? That is too expensive. Are we going to use silver to build the pots? No. If you look in your kitchen, many other pots that mommy and papi they have in the kitchen, they're made of iron. Aluminum is too soft. Okay? Aluminum is too even though we have aluminum pots in the kitchen, but iron is very strong. And that has to do with all the physical properties of the metal. But see, that's how what you were learning at the beginning of the lesson is related to this. Metals, they have low specific heat because they're going to be able to transfer the heat or change, see, that energy. When you are heating that up, they're going to be able to heat up quickly because they're good conductor. They're good conductor because they have low specific heat. Now look at the water. Water. See, if you want to do the same, let's say that you want, I'm going to compare, okay, let me use another color. I'm going to compare the aluminum with the water, okay? If I want to change the temperature of aluminum from 273 to 274 Kelvin, I need 900 joules. But if I want to do the same with water, look at this. Same 273. It's the same amount. Let's say that I have 1 kilogram of aluminum and 1 kilogram of water. Now I have 1 kilogram of water and I want to increase the temperature of the water from 273 to 274 Kelvin. And I need 4,180 joules. I'm not pretty sure about that, but I know that 5 multiplied by 9 is going to be equal to 45. So I need almost 5 times more energy to heat up the same amount of water, the kilogram of water, than a kilogram of aluminum. Almost 5 times the energy to change the temperature by 1 degree, see, or 1 kilogram of the two different substances. And that's the information that you can get from a specific heat. Okay, by looking at the specific heat, you are gonna be able to select which of the substance that you have in there is a good conductor, which of the substance you have in there is a good insulator. Let's say that you want to use, you have this, the same for materials, and you want an insulator. Are you gonna use the silver on an insulator? No, because it has a low specific heat. You're gonna use the water. Now, what is the last objective? Just to calculate the energy change. And we were talking about that before. Okay, so the energy change is going to be equal to the multiplication of the mass expressed in kilograms by the specific heat, that is expressed in joules per kilograms that are multiplied by Kelvin, multiplied by the difference in energy expressed in Kelvin. Okay, that's how you're gonna calculate the energy change. Mass in kilogram multiplied by the specific heat multiplied by the difference in temperature given in Kelvin. And over here, I'm gonna use the example that I have over here because those are the specific heats, constant values that I have. Let's say, okay, you have an example over here in the problem that you want to know the energy that you need to heat 2 kilograms of water. If you want to increase the temperature by 3 Kelvin, how are you gonna do that? You're gonna follow the same strategy that you were following when you were calculating density. Your first step is the list. Okay, you can calculate the amount of thermal energy gain by 2 kilograms. What is the information that 2 kilograms are giving you? What is that? See, kilogram is the mass. So in my list over here, 2 kilograms. Okay, now what is another important information? Of water. Okay, always when you are solving a problem involving energy change, Miramo has to give you the specific heat. So see, thermal energy gained by 2 kilograms of water. Water is another important information because you're going to be using the specific heat of water. And what is the specific heat of water? So you're going to put that over here. A specific, okay, in chemistry we use CP is 4,180 joules per kilograms multiplied by Kelvin. Let me see if my number is correct. As its temperature increase by 3 Kelvin. So the difference, and in science, just to express difference, we use a Greek letter. It looks like a triangle, but it's a delta letter in Greek. The difference in temperature is equal to 3 Kelvin. Okay? So my second step, what is the second step? You have the formula and calculations. Calculations. And you know that the energy is going to be equal to the mass multiplied by the specific heat multiplied by the difference in temperature. The mass, is that in kilograms? Look over there. Yes, so you don't have to worry about that. But let's say that the mass is given in grams. Do you have to convert that into kilograms? Yes. I'm going to multiply that by a specific heat. See, it's a given. Always is going to be a given. 180 joules per kilogram over here multiplied by Kelvin. And see, this is important. It is gain, see, because you are increasing the temperature by 3 degrees. increasing the temperature. So this difference over here is positive 3 degrees. How you gonna solve that? You're gonna multiply other numbers. When you multiply 2 by 4,180 by 3, the final answer, 2580. Sapato, uniform, 25,080 watts. The kilograms, they're gonna cancel with the kilograms. The Kelvin, they're gonna cancel with the Kelvin. And since you are calculating energy, what is the unit of measurement that we use for energy in the international system or metric system? Joules. So for changing the temperature by 3 degrees, 3 Kelvin degrees, or 2 kilograms of water, you need 25,080 joules of energy. And they are positive, because it's gain. You are increasing the temperature. Okay? So let's say that the number is to be for you. You want to convert that into kilojoules. This is the base unit. So deca hectakilo, 1, 2, 3, 25.08 kilojoules, which is the same. Okay? Now, let's say that instead of increase the temperature by 3 Kelvin degrees, you want to decrease the temperature of the water by 3 degrees. Let's say, I'm going to use the same example. Let's say that I have 2 kilograms of water. I'm going to multiply that by the specific heat. See? Joules, kilograms, Kelvin. But now, instead of increasing the temperature, I want to decrease the temperature by the same 3 Kelvin degrees. Am I going to put over here the 3 as a positive number? No. Let's say that I want to decrease the temperature from 373 to 370. So 370, which is the final temperature, 370, which is the final temperature, minus 373. If you put that in your calculator, it's going to be equal to -3. Because you are decreasing. So meaning that over here, you need a negative number. Okay? So in this example, one more time, I want to find the energy needed to decrease the temperature of the water by 3 degrees. If I have 2 kilograms of water. Answer is gonna be the same, because you're multiplying 2 times 4,180 times 3. But you have a negative in the 3. So the answer over here is gonna be the same absolute value. The only difference is the negative. 25,180 joules. Remember what the negative means? That the energy was released. Remember on the other problem, see, that we have a positive number. What does that mean? That means that the energy was gained or absorbed. See? When you are increasing the temperature, the energy change is positive because it's energy that is gained or absorbed. When you are decreasing the temperature, the energy is negative because it's energy that was released or lost. Questions about that? If you have questions about this, write your question in a piece of paper and then I will answer the question when I'm back to school. So another example. We're going to complete another example. Okay? Because I want to make sure that you know how to make this. So I'm going to start with my list. It says over here, calculate Use the formula on the table to calculate how much energy is lost. See, this is when this is turning interesting. Formula and calculation. Calculations. And then I have the answer. Okay, I didn't put that on the other example, but I'm going to put that over here. Okay. Use the formula on the table to calculate how much energy is lost by 0.5 kilograms. So I have the mass, 0.5 kilograms. Remember, that is the mass. It's not expressed into kilograms. You have to convert. Silver. So what is the specific heat of silver? 235. 235 joules, kilograms, multiplied by Kelvin. But that cool off by 2. So the difference in temperature seen is lost and is cooling off is negative 2 Kelvin. My formula, the energy is going to be equal to the mass multiplied by the specific heat multiplied by the difference in temperature. So now I have 0.5 kilograms multiplied by 235 joules per kilogram Kelvin multiplied by negative 2 Kelvin. So remember that the kilograms cancel with the kilograms, the Kelvin with the Kelvin, and I'm going to have the energy in joules. You don't need a calculator for this because if you multiply 2 by 0.5, that's 1. Multiply by 235, identity property or natural number, 235 what? Joules. Oh, mi ramo, but you have a negative there, so I have to put a negative here. If that means that the energy was lost. The energy lost by the silver is equal to, if you don't want to put over there the negative sign, you don't have to, and that's correct too, because see, when you put lost, you know that the number is going to be negative. The energy lost by the silver is equal to 235 joules. And that's how you solve problems involving the calculation of the energy change when you are increasing or decreasing the temperature of a given substance. What are you going to do right now? I'm pretty sure that you brought that worksheet that I was sharing through Google Classroom. Now you're going to get that out. You're going to start working on the problems. Because if you look on Google Classroom, that assignment is already posted.